I wanted to make this video while I was still a noob. And at this point, I've made a couple little doodads on it. I've run maybe 10, 12 parts, that's it. But I wanted to do it at this point in my learning because I wanted to give you that unfiltered view from a noob perspective. This is not to say I'm some expert, quite the opposite. The purpose here is to show you that this sort of machining can be accessible, both in terms of learning skill sets, as well as financially. I wanted to mention that it took me about a year to find this particular machine with the deal that made sense for me. But at the end of the day, this machine cost me $4,000. Like I said, it took me a long time to find that good a deal, but this thing was absolutely beat to shit. The person that owned it before really put it through its paces, but I checked the spindle, the runout was fine. You can do that with just an indicator like this that you put up against it and make sure that the spindle doesn't have huge amounts of runout. And everything worked fine except for some minor things that I had to fix, but really nothing extreme. So $4,000 got me into this machine. Again, it took me a year to find that deal. So don't think that you can go out there and find $4,000 770s all day long. That took a lot of waiting and patience, but they are out there, especially if you're fine with a beater. And on top of that, it came with the Vise. It came with actually a 4th axis, which I haven't messed with yet. It came with a lot of the tooling that you're seeing me using, as well as the tool holders. So I got in it pretty cheap. When I bought it, I don't know if the person just wasn't using coolant or liked coolant flung everywhere, but this machine didn't have an enclosure. And enclosures were almost as much as I paid for my machine if I were to buy one new from Tormach. So I actually built this enclosure out of 1/8" plywood, some plexiglass for my sliding doors, a whole bunch of silicone sealant, and also a whole bunch of aluminum extrusion that the 1/8" plywood slotted into nicely. And then the roof is just clear plastic sheeting. All in all, the enclosure cost me about $800. So give or take, I'm pushing about $5K investment at this point. That's actually cheaper than I bought my wood CNC that you've been seeing on my channel a lot, probably about 10 years ago. So deals can be found. This is an accessible extension to a hobby. If you thought a wood CNC was accessible, these can also be accessible. The first thing that we're going to need to do is design a part. Now, I'm going to show you how to do this in Fusion360. I am not going to go into a ton of detail because there are much better teachers on YouTube for Fusion360 than I. I'm just going to teach you enough to do a simple design so that we can see how that translates into programming for the Tormach and then actually executing the cuts on the machine. We're just going to build a simple little widget. It's not going to be anything useful. It's just going to teach us the necessary steps. That's it. All right, but I will try and give you some best practices along the way. First things first, Fusion360 always wants to have you create things as components. Think of a component as a independent piece of a potentially multi-piece product. We're just going to build a single component, and we're just going to call it widget. In order to build your components, it's going to have you draw sketches, which are going to be 2-dimensional drawings on a given surface or plane, and then it's going to allow you to do 3D modifications to those sketches to actually start building out your part. So after we've got our widget, the next thing we're going to do is to create a sketch. and it's going to ask us what plane we want to create this on. So you can choose X, Y, or whatever. If we had already had some drawings here that have been made 3D, it would actually let you choose surfaces of those 3D objects to draw on as well. So that we'll actually see in a little bit later. But let's just choose our XY, and we are going to build just a simple rectangular object. For most of the things that we draw, it's going to walk you through literally the steps. So the first thing it's going to say is place your corner. All right, we're going to choose our origin as our first corner. And then as I drag it out, you'll see that it's highlighted the first of 2 dimensions that it wants in order for us to be able to define our rectangle. So what I want to do is I want to make sure that this widget fits within the piece of scrap that I've cut off. So I'm going to make sure that it's no bigger. So we're just going to say it's 0.45 wide. And I'm going to hit tab, and it's going to go to that second one. And I know that I don't want it longer than my piece, so I'm going to just choose 1.25. We'll actually see what the piece looks like in a second when we do our CAM programming, and so you'll understand a little bit better why I'm choosing the dimensions I am. But I can hit enter, and that's going to draw my square. And one of the interesting things about Fusion 360 is when you get more advanced, you don't actually have to put in concrete numbers. You can actually use variables, and then you can change those variables to meet your needs in the future. For example, you can scale up and down parts, and they will redraw themselves accordingly. But what you need to keep in mind in order to leverage those capabilities in the future is you need to have a fully black bordered object. So if I draw a circle here, for example, notice how that one is not a black bordered object. It's a blue bordered object. And the reason for that is it's not fully what is called constrained. So really what constraints are is it needs to be anchored to a point, and being on a plane does that for a couple dimensions, but it doesn't do it for all of them. And then it also needs to be constrained in terms of its size. So really, the reason this one is black is because we anchored it to our origin, and we fully defined what our dimensions were. And by nature of being a rectangle, it has these things which show us that these happen to be parallel across here and across here. So it's fully constrained. There's no ambiguity in that shape. So how can we constrain, for example, our circle? Well, first things first, I can hit D, and I can go ahead and define the dimension of my radius. So I can say that this is a 1-inch radius, and that's going to define its size constraint. And then the other thing that I could do is I could say, okay, well, I want to lock it to a position on our coordinate plane to finalize that constraint. So we're going to choose coincident as a constraint, and I'm going to say I want this point to be coincident with that point, and boom. Now you can see that it turned black because it does happen to be fully constrained now. That's about as deep as I'm going into constraints. That is a giant rabbit hole that you should absolutely learn if you're going to use Fusion 360, but just understand that constraints exist. It actually helps you draw, but also it's good practice to have fully constrained sketches anyways. So keep that in mind. And not only will it tell you whether your sketch is fully constrained here by making things black bordered with a light blue hued fill, but also if it's fully constrained, you'll actually see the lock on that icon next to your sketch name, which let's go ahead and name our sketch here. Let's call this base shape and hit enter. If I were to say, draw something else, let's do another circle real quick. Notice how I have an unconstrained shape in my sketch, and therefore it now is an unconstrained sketch icon over here as well. Let's Control Z to get rid of that. And actually, let's just go ahead and Control Z to get rid of all this stuff, which we don't need. And obviously I got rid of my name, so let's just call it base shape again and hit enter. Okay, we are going to finish our sketch though, because again, we're keeping it very simple. And it's going to zoom back to our standard view. You can always move things around by clicking on things up here or dragging things, but if you want to get back to that standard view, you just hover over the cube and hit home. Okay, we are going to now make this rectangle into something that we can actually use. There's a whole bunch of modifications under our solids modeling that you can do, but we're going to do a very simple one to create our first shape before we do any mods, and that's going to be to extrude a shape. So again, it's going to walk us through the steps. I had already selected this rectangle, so it knows, but I could, let's say I didn't, and it wants me to select as the first step. I'm just gonna select it, and then it's going to ask me, do I want to extrude it one direction, two directions, symmetrically in two directions. Again, this isn't a full tutorial on Fusion, there's better ones out there, but just to get us going, we are going to extrude it one direction to a given distance. The distance that we are going to extrude that is 0.25 inches, and you'll see it automatically responds to that. And I'm going to have it create a new body. So whereas a sketch is a drawing that we will use to define something we build later, a body is going to be an actual 3D object that we can go and cut out on the Tormach. So I'm gonna hit OK, and you can see now I have my wonderful body. And if I expand that section, I have body 1, which we will call Tormach object, and enter. Okay, obviously this is not a very exciting thing to cut out. So we are going to do a couple more modifications to this just to make it a little more exciting. I'm going to create a new sketch and show you that I don't have to pick a coordinate plane, but like I said, I can actually pick one of the faces of my object. So I'm going to pick this top plane of our object, and it's going to allow me to create stuff there. I'm going to just randomly place a circle, and I want that circle to be 0.3 inches in diameter. And it's not going to be fully constrained yet, but I can hit D, and I can say I want the center of my circle to be a certain distance from this edge, and I'll place it, and then it'll ask me how far. And I want it to be, let's say, 0.35 inches. And then I can, still with the dimension tool on, I can say I want this center to be a certain distance from this edge. And let's just say it's 0.25 that I want. Great, that's one way of doing it, and now we see that we're fully constrained. I'm gonna show you one more thing. I'm gonna get rid of this dimension here, and let's hypothesize that we wanted our circle to be on the center line vertically. So what I'm going to do is I'm going to create a line. I'm going to do a quick modification here from line type. I'm going to say a construction line, because I'm not going to use it to cut anything. I'm just going to use it to help myself out. And you'll see that the cursor snaps to stuff as we're working. It'll also snap to that triangle, and that is to snap to a midpoint of a line. And so I'm going to click there, and I'm going to say snap to the midpoint at the other side, and hit enter to get out of the line. And you'll see that dotted line means it's a construction line. And then what I'm going to do is I am going to say that I want our a midpoint constraint. So I want the midpoint of this to be the midpoint of this. And you'll notice, I failed. Why did I fail? Because I've already told it that it's 0.35 inches away from this edge. And so if I tried to make that the midpoint of this line, it's going to conflict with that. So I drew my line incorrectly, because remember, I wanted it vertically midpoint. So let's undo, let's get rid of that line. I'm gonna create a new line, again, construction type, but this time, I am going to make my line like this. And it doesn't really matter where I put that line in the grand scheme of the object, because I've already constrained the circle to this distance from the edge. So when I tell it to match the midpoint of that line, it's just only going to move it vertically. Let's see how that works. I'm gonna go back here and I'm gonna do midpoint. I'm gonna click the circles center, and then I'm gonna click my construction line, and boom, you see it's moved it up to the center, and we now have a fully constrained object, or fully constrained sketch, sorry. All right, let's finish that up, and let's hit E for extrude one more time. And I'm going to choose, you can see it highlights things. I'm going to choose that circle we just drew, and I'm going to say that I want to basically create a pocket that we're going to route. So I'm going to go down, negative, and let's go down 0.125 inches, an eighth of an inch. And you'll see that it's smart enough to automatically notice that since I'm going down into an object, it changed it from new body to cut. So I'm going to use that circle to cut away material from the object I've already created. And if we had multiple objects on our screen, we could validate that we're cutting the widget object only. Click OK, and you'll see that it is created a hole in my widget. The other thing I'm going to do is I'm going to show you how, if you don't like something, you can modify it. One of the cool things that Fusion does is it keeps a history of everything that you've done. And so you can actually change stuff. So for example, I can go back to my original sketch, either by double clicking here or by double clicking the base shape. And let's make this instead 0.4, let's just be crazy. Let's make it a whole inch, a lot bigger, save my sketch, and boom, that's still in the center. It's still 0.35 from that edge. So Fusion's really smart about things like that. And that's one of the very powerful things that you can do with this software. But let's go back to normal, or let's modify something recent. Let's double click that. And I can say instead of 0.25, I just want to go 0.2. And voila, we are back to finishing that object. Okay, I'm going to show you how to next fillet corners. So let's say we didn't want sharp corners on these edges. We wanted something nice and a little more graceful. So I'm going to hit fillet. So we're now in the modify properties. And I'm going to hit shift and select all the corners, and I can select them through the object too. I'm going to select all these corners that I want to do a fillet on, because again, it's walking me through it. First things first, it wants me to select. I'm going to have a constant radius fillet, and then I can actually enter the value, and this is going to be the radius of that fillet. So let's do a 125, so an 1/8 inch radius, and you can see it mod there. Or if we wanted 0.625 for a 1/16 of an inch, we could do a tighter radius like that. But I want something nice, and so we will do a 0.125. Hit enter. I'm going to show you also how to do chamfers. So we can cut the edges of our objects so they're not sharp on the top and bottom, but I'm actually not going to keep those chamfers, and I'll explain why when we do our cam. But we can go to modify, chamfer. I can select the edges, or I can select the entire face as well. That's another way to do it. If I select the edge, it's just going to do the edge. If I select the face, it's also going to do the edge of the circle because that touches that face. So let's choose this edge, and let's say we want a chamfer of 30 thousandths of an inch, and you can see it's going to go ahead and do that chamfer for us and put it in the model. The problem that we run into when we model our chamfers is that it makes our cam a little more difficult. You have to end up, actually, we'll keep it. I'll show you why. We'll do chamfers on the top one way and chamfers on the bottom another way. this is the object that we are going to build. Nothing fancy. So we are happy with what we've designed, and so we're going to change from our design workspace, and let me just name this for good measure. Call it circle on top. Sorry, I just like having things named. We're going to go from design to manufacture. And this is where we're going to do all of our setup for how we are going to cut things out. Just like we had components and sketches in the design workshop, in the manufacturing workshop, we're going to have setups, and those setups will have paths. So a setup is basically just defining where on the machine you're going to place this thing you're cutting out, where your X and Y is, and also defining the size of material that you're going to cut it out of. So let's start by doing a setup, and I'm going to say that I want my Z0 to be the top of the stock that I'm going to cut. I could also choose, say, the top of the object itself, but I like to use the stock as my reference. And I'm also going to use the edges, the front and left edges of the object, that the stock that I'm cutting out of, as my XYZ. So I just click that edge, and that's about as deep as we're going to go into the setup tab of setup. When it comes to stock, I'm using fixed sized pieces of aluminum. So I'm going to say it's a fixed size box. And for the XY, I generally like to keep my model in the center position of that stock so that I'm cutting equal amounts off all the edges, because especially if we're cutting something that is very close to the size of our object, that diminishes my risk that I'll screw up. But we're going to input the actual sizes of the piece of metal that we're going to cut out. So if I take calipers and I measure the block that we're going to use, I've got 1.374 inches for my width. So 1.374. And for my Y depth, I have 4.89. Sorry, 0.489. And then for our height, or thickness, sorry, of our object, I've got 0.359. So we're going to say 0.359. Now, I said I like to keep my object in the center for my X and Y. I don't like doing that for the Z. And the reason being is we're going to have to clamp this object in a vise on our CNC in order to hold it for the milling. And so I actually want to leave as much stock on the bottom as possible so that I've got a lot to clamp onto for the majority of our paths. And then when we flip it over to do the back, we'll mill off all that excess and chamfer the back while holding onto the actual object itself. That's easy when we have parallel sides. Obviously, if you have a non-parallel sided object, that's going to be a little more difficult. But what I'll do is I will say I want to offset it from my top, and I'm just going to offset it by 20 thousandths of an inch. So you see here, I've got a pretty decent amount of stock that I can hold on to in my vise. If my model is 0.25 inches thick, I've got 20 thou on top, that's 0.27, and if we minus 0.27 off of here, that leaves me about 80 thousandths of an inch to grab onto, which for an object of this size is going to be plenty for our purposes. Great. So we've got our first setup, and I'm going to call it top. Okay. The next thing that we're going to do is start creating paths, and we know that we have 20 thousandths of an inch of extra material on the top. You can see it there, it's that. And so we are going to face material off of this. First things first, I'm going to select my tool. We'll talk about feeds and speeds in a minute, but I've got a library of tools already here. We're going to use my nice Superfly from Tormach as our tool. I manually turn on and off my coolant, so I'm not using the machine to do that, but you can. This is all filled in for me by nature of selecting the tool, provided I don't want to modify. And then we're going to select the geometry. If I don't select any geometry at all, what it's going to do is it's going to assume that I'm going to want to mill the entire stock, which when we're facing is exactly what I want to do. So I'm not going to select any curves or faces or anything as my geometry, because that'll restrict where we cut. And I want to mill 20 thou off the entire face of the top. Instead, what we're going to do is we're going to use the heights in order to say how we want to cut things. So our retract height is how high up it, you can learn all of this. The two that we're going to focus on are my top height, which is where my stock is, and that's this light blue line here. And then my bottom height is how deep I'm going to mill into this stock with this particular path. And the model top, remember, is 20 thou down. And so if I create my bottom height being the model top, it's going to cut from my stock top to my model top, which I know is 20 thou. So that's perfect. I know that my Superfly is perfectly capable of taking off 20 thousandths in one pass. And so I'm not going to do multiple depths, but let's say for some odd reason I wanted to, I could say only take off 10 thou per pass, and it would do it in 2 passes. But again, 20 thou is just fine for us. And linking, I'm not going to get into, especially for this particular process. Click OK, and it's going to calculate out our path. All right. We glossed over some stuff when I talked through that. So let's address some of it. My tool library. I have a library of tools that match stuff that I actually have ready and set up in my machine, good to go. I recommend that you do this as well, especially for the really common stuff that you use on a regular basis. And so what you do to create your tools is you come in here and you say, I'm going to create a new tool. I like to create it in just a standard library for myself. And you're going to choose the type of tool that this is. So let's just create something simple, like a flat end mill. And give it whatever name you want. It's going to put the diameter in the name automatically. So I like to use the description more for non-size defining characteristics, like let's say it's a 3 flute flat end mill, and we're going to call this just test because I'm doing it for y'all. And then we'll define the cutter. So it's 3 flutes, let's say it's carbide, 1/4 inch diameter, 1/4 inch shaft, overall length. And when you click into these things, it'll actually show you what it's talking about. Length below the holder, let's say that it only sticks out 0.5, because the lower the stick out, the less deflection we'll have, and therefore the more rigid the tool will be. And let's just say that it's got a 0.3 inch flute. This is really cool because it'll tell you where you potentially have problems when you do a path with it. If you try and cut, say 0.4 inches with this cutter, it'll yell at you, or it'll show you weird stuff in the simulation. The next thing we're going to do is we're going to define our cutting data, and that's going to be, well, you can define the shaft and the holder if you really want like to model this gray area here. I don't really bother, but if you're doing like complex work holding, sometimes knowing the holder size and shape is good, just in case you might hit something with it. But for our purposes, we're not going to. We will discuss feeds and speeds in a little bit. Just know that this is where you enter your feeds and speeds. You can make recommended step downs. For example, if for my fly cutter, I like to do no more than 20 thousandths, so I can do that. If you only want to cut a certain percentage of your diameter, you can give it norms for its step over. If you're automating your coolant, you can do that as well. So keep that in mind, but we will do feeds and speeds a little later. The only thing left is what we want to do for post-processing. This is where it actually matters for the Tormach, because the Tormach, it's going to force you to do manual tool changes, unless you have an automatic tool changer, which is several $1,000s, which I do not have. So we're actually going to tell it the tool number, and actually for automatic tool changers, you would as well. But the reason we're going to do that, let's call this tool 15, is because if you've got multiple tools being used throughout this process, it's going to actually tell you on the Tormach screen when we cut, like, hey, have you put tool 15 in? And it's not going to let you pass that query without saying, yes, Tormach, I put tool 15 in, because that's going to do a bunch of calculations to make sure that you're not going to just crash your machine into material and tools and whatnot. So really important to track your tools. We'll do the Tormach side of the tools a little later. You can click accept and you'll see now we have this tool available to select. Obviously I don't want that in there because it's a fake tool, so I'm going to delete it. But that's how I entered all of these. Okay, the next thing that I would highly recommend that you do is simulate all of your paths. There's a whole bunch of parameters to do here, so we want to make sure that we're not screwing up. And so we're going to right click and hit simulate, and it will actually, this is the speed of the simulation here, and we can hit play and it'll actually come through and it's going to pull that top off, and you'll notice some colors changed. The blue is my stock, the green is my actual piece. So what it's telling me is once I skimmed 20 thou off, this is the actual top of my piece, and the blue is stock that we still need to remove with other things. Let's run that simulation one more time, because with facing, I really like to view it from the front, because you can actually see it cutting off that depth. It's going to come in and you can see, boom, it pulled off that 20 thou, and you can visually watch that 20 thou come off. Great. Really like that. Let's go and do our profile path. We are going to do an adaptive clearing path. And what we are going to clear is the excess around. I'm going to do that with just a 1/4 of an inch 3-flute end mill. Again, all my feeds and speeds get put in automatically. And this time we're going to choose geometry because I actually want to cut to the shape. We are going to take this edge down here or this edge up here. Doesn't really matter. It's just simpler for me to choose the edge down here because it's going to know how deep the object is since I chose the bottom edge, which is yet another reason why not modeling a chamfer in on the bottom is beneficial to us here. Because if we had modeled a chamfer in on the bottom, it would have been whatever the depth of the chamfer is above the bottom of our object. But I'll choose that, and you can see the blue saying, hey, I'm going to cut off all this other stuff outside of it, which is exactly what I want. And you see here the bottom height is now our selected contour. If I had selected instead this edge here, I could have just said model bottom. That would have worked as well, but cool. It defaults to leaving some stock. I'll talk through that in a second when we do the next path, but I am going to leave radial stock, so thickness and width. I'm not going to leave axial stock, which would be stock on the bottom. I don't care because that's just going to get cut away. And I'm happy with all the other defaults here. So let's run this. And again, let's do a simulation. Slow it down a little bit. And awesome, it's going to come in and it's going to start pulling things off. And I like these adaptive clearing paths because they keep a constant engagement of the tool, and that's going to be good both for tool life, but also if you're using small diameter cutters, it's going to minimize the risk that you end up snapping a tool. All right, and you see there that it does still have blue around the edge because again, we told it to leave 20 thousandths of an inch. The reason for that is I have had experiences where the adaptive clearing paths, because of how they kind of come in, they can leave non-perfectly smooth edges. So I like to use an adaptive clearing path to clear out most of the material, and then I'm going to come in and I'm going to do a 2D contour. I'm going to choose the exact same bit. It's going to default to keeping it. The exact same contour. I'm going to choose the exact same heights, but here you'll notice I'm not leaving stock. And what that's going to do is, I call this onion skinning. It's going to take off that just onion skin, that last 20 thousandths, and it's going to do it in a nice smooth motion. To make it extra smooth where it comes in and out, I'm also going to set the degree that it enters the material and exits the material from 90 degrees, so coming straight in and then zooming around, to coming in at a 45 and then zooming around. It'll make it nice and clean, and make sure that perpendicular is turned off, and click OK. And you'll notice that every time that we add a new path within a setup, it's going, if I click on it, it's going to assume that all previous paths have been run and show us how the setup looks at this point in time. So let's simulate this, and you can watch it come in at a 45 degree. It's gonna pull that 20 thou off, and you'll see that my edge is now green, but there is a little blue. That blue is telling me, hey, that chamfer, you haven't done that yet. So that's what it's showing us. But my edge is looking nice. I try and get all of the same tool done at the same time. And so we're going to do this hole next. There's two ways to do this. If you wanted to, say, do it with an adaptive clearing path, you could do that. Or there are 2D pockets. The difference between the pocket and the adaptive clearing is the pocket will create paths parallel to your edges. You can kind of see it in the thing there. And the adaptive clearing, again, does that constant radial engagement of the tool. If this was a non-uniformly circular pocket, I might look at doing the adaptive clearing, or if I was using a really small diameter bit, I definitely would look at doing adaptive clearing and then maybe do an onion skin at the end. But for this particular purpose, I'm happy doing a 2D pocket. So we are going to, again, same tool. We're going to select the bottom of this. You could have also selected the wall. It would have changed a couple things, but I'm going to select the bottom. And the reason for that is it's going to set my bottom to that selected contour. So it automatically knows how deep I want to go. I can obviously modify that if I want. And that's an interesting thing. The fact that the CAM will let you cut things other than what you modeled. What I mean by that is I could say, okay, I want to mill to the selected contour and then add another 0.12 inches. Like, that's odd, kind of, but it'll let you do it. But we want to go to the selected contour. I don't want to leave any stock. I want it to cut the actual full shape. And the one thing that's going to be fun here is how we go down into the material. In metal, you really, unless it's a drill, you don't want to slam the bit just straight down into the material, and so we can choose how we want to go down. Helix, we can do a zigzag, but helix is a pretty good one. All right, let's take a look at what it does. So, oh, look at that. We've got a problem. It didn't actually code anything. We have an empty tool path. So we have a 1/4 of an inch bit. And what size was our hole again? Our hole was 0.3 inches. I know what our problem is. that helix isn't going to let us put a 1/4 of an inch bit down into that hole. The helix is probably greater than that hole's diameter with that bit. So there we go. Look at that. So we've got a 1/4 of an inch bit doing a helical ramp diameter of almost a 1/4 of an inch itself. Let's see what bumping that down to about 50 thou does for us. Is that enough? Not quite. All right, let's go even smaller. Let's do where was that? 50 thou. Let's do 25. See if that's good enough. Nope, still too much. Let's do 20. All right, I'm tired of playing this game, and I don't want to put a tiny helical ramp in here. So we're going to bump this back up to 50 thou. I could instead do a different tool. I could do like an 1/8 of an inch bit, but I don't want to do too many tool changes for y'all. So let's go back to our design, and since this is just a widget that we don't care about, I'm just going to make this a larger circle. So we're going to call this 0.37. Let's see what that looks like. Yeah, that's fine. Cool. Yeah, you'll see it's going to warn me that I've changed stuff. So I'm sure there's a way to rerun them all, but I just double click them and then I rerun them so that they're green check marks. And now we should be able to, I'm going to reselect my geometry just to be safe, and we're going to look through everything and make sure that we're happy. And let's see if that 50 thousandths ramp is allowed now. Man, it still doesn't like this. Oh, it's probably this minimum ramp diameter that's hurting me as well. Let's see if that helps. There we go. All right, now it's allowing it. You can see that tiny, tight little helix. Let's see if we can't make that better now that we found that problem. Let's see if we can't get away with at least a 50 thou. Oh, much better. And from what I'm seeing, we can probably even get away with bigger than that. That was the problem. Let's do an 80 thou on both of those. Cool, that looks much nicer. And as always, let's go ahead and simulate. It's gonna come down, it's gonna helix, and it's gonna start above it so that it's got a nice helix going on as it hits into the aluminum. You can see it's cutting away. And once it reaches the bottom, it'll go out and it'll get rid of that extra diameter around the edges. Cool. All right, last thing that we're going to do for the top is we are going to do our 2D chamfer. Now, the reason I don't like modeling the chamfers is because when we do a 2D chamfer that's been modeled already, I'm going to choose my chamfering 45-degree 1/4 inch bit. When we go and we choose our geometry, no matter which we choose, the top or the bottom, it's going to force us to do something a little wonky. I'm going to go ahead and hit OK, and you'll see it's going to throw an error. Again, empty tool path. If we click on it, it'll give us some recommendations. If you're machining a chamfer that is modeled, try setting the chamfer width and chamfer clearance to 0. So we can go in here and we can say, where is it? Chamfer width and chamfer clearance to 0. The tip offset is how far the tip will be outside of the thing, and that's a good practice to not have the tip follow that edge. So now that we've set it to 0, you'll see that it'll run just fine. And if we simulate it, it'll look good too. It'll come in. I'm just gonna zip around, and now finally everything for our part will be green except for the excess material at the bottom. The reason I don't like doing chamfers like this is it gives you less control. If I model in the chamfer and then I have to set those two values to 0, I can't change how I want my chamfer to look in the CAM. I'd have to go back to the design, change my chamfer. Whereas we'll see on the bottom, I have a lot more control. The other thing I'm going to do is I don't like perpendicular lead-ins on profiles. That's just me. So again, I'm going to change that to 45 so that the chamfer comes in and exits at a 45-degree angle. Ugh, that's, oh my God. That's another thing I just remembered. When you do the modeled chamfers, it doesn't let you play with that either. Yet another reason I hate it. Okay. But we'll see the ability to do that on the backside. So let's do a second setup. We are going to choose that same corner, but we are going to flip it over because we want to literally flip over our piece. And so now our Z needs to point up, and we will change the X and Y to be there. So we will actually 0 on the stock from the right and the front now instead of the left and the front. And the reason for that is once we flip it, this corner was what was previously over there. For stock, we're just gonna keep it from preceding setup because it's gonna be smart enough to know all the things that we've already done here, apply to here, and hit OK. Okay, we are going to only do 2 paths here. We are again going to do a facing path. We are again going to use our fly cutter. And we are again just going to do model top. And it's the top now because it's been flipped over. So it's concerning the what was previously the bottom, not the top. And our stock top is where we start cutting. And I am going to do multiple depths because we're taking off a lot more this time. So I'm going to limit it to my default that I put for this tool as 20 thou and hit OK. And you'll see it's going to take multiple passes this time. If we do a simulation, we can watch it. It's going to go back and forth a couple times. Let's make it faster than this. It's going to go back and forth a couple times to take off multiple passes at 20 thousandths an inch per pass. Cool. And last but not least, let's do the actual nice way of doing 2D chamfers that I like. We are going to, again, you can either choose the face or the edge, but let's choose our chamfer tool. For our geometry, let's choose this edge. And now I actually get to define not just that we can enter at a nice smoother 45 degrees, but I'm actually going to tell it how big I want my chamfer. So I could do 30 thou chamfer, I could do 20 thou chamfer. I've got a lot more control now. And so if I hit OK, it's going to model in that cut. And so again, I've got that control. Now, when we simulate this, something weird is going to happen. It's going to look like we're taking a giant chunk out of this material, and it's going to look like we're just plunging this bit into all of this stock. But remember, it's only showing us the material based on this setup. It's not remembering that, hey, with these paths here that you did first, you already removed all of that. I'm sure there's a way, I just don't know how to do it yet. And you'll also see that there's a red line around my chamfer. The red is saying that I've removed material that does exist in my model. So whereas the green is saying, you've perfectly matched the model. The blue is saying, there's still stock. The red is saying, you took stuff off that you didn't model. And again, remember, we didn't model the chamfer on the bottom, so it's being honest. It's saying that, hey, look, you're potentially doing a mistake here, and we're going to highlight it in red. but that is not the case. I actually want that removed, so I'm very happy. And we are now done with all the paths in order to create our tool. And so we need to export them. And with the free version of Autodesk, which you can use if you don't make more than $1,000 a year using it, which I don't, I'm a hobbyist, I don't sell anything. There is one limitation. It's not going to let you build a file that has multiple tools. So for the top, we have 1, 2, and 3 tools, and for the bottom, we have 1, 2 tools. So you do have to export on a per tool basis. So we're going to hit right here, we're going to say create NC program, numerically controlled program. And we can give it a name. We're going to call this top face. We're going to choose our path. I'm going to use a flash drive, and I'm going to just call this test, and I could go and save this here. The most important part about this, though, is choosing your post. So what is a post? That is the instructions that you tell Fusion360 to use to make sure that the program matches the machine that you're cutting with. And since we are doing a Tormach with PathPilot, I choose the Tormach PathPilot post. If you're going to have to add this to your options, so what you would do is you come here for the first time ever and there wouldn't be any options. So you would go choose from library, and you can actually go to the Fusion library, and it's got a whole bunch of stuff here. If you were to look around, there's all sorts of machines. If you've got anything common, they've generally got it. And so we would go down to the Tormach and just choose Tormach PathPilot. If you're using any Tormach that is, I think 2015 and newer, it runs PathPilot. And as long as you're using a mill, not one of their other things like turning, etc., it's going to be the Tormach PathPilot one. And if you just select that, it would then become one of your options to choose. And then you click post and to save it to your drive. Now, the only other thing to keep in mind is you can select multiple paths when the tool is the same. And so we could create a program for this one. This would be like all our T3 paths, and I could post that. So really, even though we've got 5 paths for the front of the object, I'd only be running 1, 2, 3 independent programs, then we would flip it, re-zero, and then we run 2 independent programs for the back. There's 3 main ways in order to get feed and speed data. The first one, and which is where I started with my learning journey, was to simply go to a manufacturer of a bit that I'm using and see what they recommend. They'll oftentimes have sheets. Sometimes each individual bit's page will have recommendations, but a lot of manufacturers will give you recommendations. In the case of Ondrad, they have the various types of bits that you can buy on a matrix with their diameters, and it tells you what chip load you should be looking for. A quick piece of information about chip load. Chip load is literally the thickness of the chip that is cut by the cutter, given some other criteria, such as the feed rate, which is how fast it moves through your material, the RPMs of your spindle, and the number of cutting edges. And you'll see that there is a range with all the recommendations, and also if you're cutting more than 1 diameter's amount deep, they're also going to tell you to reduce chip load as well. And that's truly cutting that much. It's not, say, I cut 1 diameter deep and then I cut a 2nd diameter deep. It's truly the amount cut. So you'd have to cut 2 diameters deep to want to reduce by 25%. This is fine for a lot of work. The problem is what happens if you don't know the recommended RPMs for a given material? Some materials really don't like fast RPMs, some like really slow RPMs, and vice versa. This doesn't really help you there. So there's still a set of knowledge that is not shared on this sheet. Also, sometimes the ranges for chip loads are huge. So this is 100% difference in range. You could be down at the 0.004 all the way up to 0.008. So again, big learning curve here. Like I said, this is a fine place to start. But once you start getting a little more advanced, you're going to want to probably look at the second method. And the second method is just adding an additional formula to these particular calculations and recommendations shown here. And that is understanding surface feet per minute. Surface feet per minute is a recommendation on a per material basis, how fast that material likes to be cut. That is going to help you define the appropriate RPMs, and in some cases, it'll also kind of give you feed rates as well for specific materials. So let's say that we're cutting 6061 aluminum, we would look up the surface feet per minute surface feet per minute recommended value for that material. We would use that to calculate the RPMs that we would like to use. And then that's going to allow us to finish out a formula like this to find the chip load that we are looking for. All of the outputs of these formulas are what we put into that tool library in Fusion360 that we saw earlier. The number of cutting edges, the RPM, the feed rate in inches per minute that we're sending through the material. And we don't actually enter the chip load, we're just calculating the chip load with these to make sure it's within the recommendations. Let's do a concrete example to make sure everyone's following along. At the top here, we have the formula for surface feet per minute and how it relates to RPM. If we look up the recommended SFM for 6061 aluminum, it has a range of about 2100 to 2840 for carbide tooling. We want to be conservative here, so we're going to pop that 2100 value into our formula, and we get a recommended RPM of 16,050. If we then go and solve for feed rate using the formulas we saw on the previous sheet, we come out with a recommended feed rate of 288.9 inches per minute, assuming a 1/2 inch diameter tool, which is the same that we assumed for our first formula here, and also a chip load on the conservative end of one of the recommendations for one of the bits we saw on that previous screen. So again, twice we've been conservative, and we ended up with a crazy feed rate. I'm going to hazard a guess, none of the people watching this have a machine that's capable of doing rapid moves at that speed, much less capable of cutting things at that speed. So already we've got a problem. Secondly, if you're running a Tormach, chances are you don't have a high-speed spindle. There are some, but most of them no. And so you're not going to be able to cut at 16,000 RPMs anyways. You're probably maxing out at about 10,000 RPMs. Okay, well, we can rerun that calculation using that RPM value instead. And that brings us down to 180 inches per minute, which is still pretty quick, but at least it's something that's in the realm of feasibility for some of us. But we've already done a compromise 3 times. We were conservative on the surface feet per minute, we were conservative on the chip load, and finally, we basically took 50% of our RPM off, so we're now extra conservative, and we're still ending up with a pretty fast feed rate. Okay, let's assume that you're doing this calculation not for a Tormach, but say a desktop CNC optimized for wood and plastic. So you might actually have a spindle that goes up to 18, 20,000 RPMs. However, those machines sure as heck aren't going to feed rate at 288.9 inches per minute either. So what can we do to modify the formula again? Well, we can lower the number of flutes that we're going with from 3, which is generally the recommendation for aluminum, all the way down to 1, which is what a lot of people use on these hobby desktop CNCs because it actually gives you a number that you're capable of cutting. In this case, 96.3 inches per minute becomes our new recommendation. I also don't think if we're cutting in aluminum that you're going to get away with a 1/2 inch bit on one of those machines. But again, we're starting to see that a lot of these recommendations are really geared towards heavy duty industrial machines and not really towards us hobbyists. And that's why you immediately start to see problems with these numbers and these methods of calculation. You numerous times have to be extra conservative, and that's going to really start adding some question marks to whether you're using the right values, because where do you compromise? That's something that you learn over time and through experience. And also, if you're not optimizing cuts, you're not optimizing your tool's lifespan either. You're risking breakages. So that brings us to why I finally stopped doing it this way, and I spent the 70 some odd dollars and I just got something called G-Wizard, which is the 3rd method that we're going to discuss. And the reason I recommend G-Wizard is it takes a lot of this stuff into account. It'll take your max RPMs of your machine into account. It'll take your max rapid and cuts into account. For feed rates, it will take the rigidity of your machine into account. And it's going to do something that none of these calculations do. It's also going to take into account how far out of the spindle your tool sticks, because deflection of tools is a big thing. And if you've got a thin tool, a small diameter tool that wants 1/1000th of an inch chip load, and you deflect 1/1000th of an inch in the cut because you're sticking out far and it's allowing that deflection, you've now increased your chip load by 100%. So I've found that my risk to losing tools to breakage and other problems was drastically reduced by going away from these traditional methods and going towards the calculator from G-Wizard that I'm going to walk through now. This is G-Wizard, and there's really only 2 sections that we're going to concern ourselves with. We're going to first start with CAD CAM and then come back to feeds and speeds. CAD CAM is really simple. You tell it the type of thing that you're trying to cut, pocket, 2D profile, etc. You tell it the depth, and if there's inside radiuses, you give it the minimum diameter of that radius, as that's going to be your limiting factor in terms of the size of bit you can use, at least with internal radiuses. For external stuff, you have to tell it internal. But let's stay on pocket and hit calc. And as you can see, it's going to give me some suggestions. It'll tell me my RPMs I should be using. It's going to tell me the size bit, the type, number of flutes, whether it's roughing or finishing, how I should enter the material, if there's a different entry feed than there is for my cutting feed. All of this good stuff with 3 pieces of information: type of cut, depth of cut, inside radius. One of the negatives that comes out of the CAD CAM section, though, is sometimes it will suggest things that you do not have in your tool arsenal. For example, let's say that I bumped up my inside radiuses to 1/2 of an inch. Let's say I don't have a 3 flute 3/8 inch carbide bit. That's going to be a problem for me. So that's why, secondly, we will go to our feeds and speeds calculator. You can set up a machine, and that's going to take into account some of the specifics of that machine. For example, my horsepower limit of 1, my feed limit of 135. But really what you're doing from here is simply selecting the material that you're going to cut, and there are a ton of them, whether it's carbide or some other material for the end mill, tool diameter, how many flutes, and here, the really important part, we're going to play with this in just a second, how far the tool sticks out from the actual collet that's holding it. It's going to give you some generic information based on a lot of manufacturers' recommendations, but what we're really concerned with here is telling it how deep we're going to cut, and also the width of cut. So if later in the program you're going to watch me cut out a adaptive toolpath, and those adaptive toolpaths keep constant radial engagement, and so you can actually set a radial engagement. That's the amount of width in terms of the diameter of the cutter that is going to be engaged at any given time. A good way to think of it is if you're slotting, you have 100% engagement, obviously, and that's why if you hit slot, it does the full tool diameter as your engagement. But what it's going to do is it's going to immediately spit out what it thinks you should use in terms of RPM, feed rate, and if you need to do an entry like a helix or a plunge, it'll give you specific feed rates for that too. So while the CAD CAM section gives you recommendations for bits, if you want to run a custom bit, you can hit the feeds and speeds, enter your parameters, and it's going to give you all of that same information that you can run with. It'll also give you some tips like using climb cutting, what coatings are good, whether you should use lubricant, etc. And you can also change how aggressive you want things to be. So let's say we're trying to be conservative and it's a finishing cut, you'll see it drops down the feed rate but increases our RPMs, whereas if we go full aggressive roughing, it goes back up in a lot of things. What I really want to point out though is, firstly, this is really fun. It tells you when you're getting close to your limits. And then the other thing that's really cool is it calculates deflection, and that is really what this stick out is helping with. So for example, here I don't have a problem with deflection. We're only deflecting at 2% of my 1,000th chip load deflection rating limit. However, if we say we're working with a much smaller bit and we had it sticking out a whole bunch, you would see that, wow, I am way over that limit. We're deflecting almost 3/1000ths of an inch. But look what happens if I get rid of half of that stick out. Boom, now I'm only 45%. So that stick out is an extremely important piece of information that I've never seen addressed in feeds and speeds calculations anywhere else. That is what's going to save your tool life, and that is what is going to stop you from breaking a lot of bits as far as I'm concerned. So if you've ever broken 2 bits, you've already paid for this, so you might as well just buy it. And they haven't given me any money, I bought it myself. They have no idea who I am, so I just like it. Go ahead and turn on power to your entire setup. Wait until the software has completely turned on. I don't know how much truth there is to that, but I've heard that turning the machine on prior to the software fully booting can cause some hardware problems on the machine. Once you have the software ready, you can turn off the e-stop and start up your machine. You can then take the machine out of reset and it's ready to start moving. First thing we're always going to do when we start up the machine is reference Z first and then YX. I'll click them while the machine is doing them so you can see what it does. The machine now knows where the table sits and the spindle sits based on the limit switches. So now we can start getting to work. One of the most important things when it comes to working with metal is how you hold your workpiece. There's a lot of ways to do that. You can use specific jigs, you can have fixture plates, but one of the most common is a simple vise. Get a quality one. There's a bunch of cheap ones out there that really aren't square, so you're never going to be able to get this bottom perfectly level, and then your parallels won't work correctly. They're a nightmare. This is one of the places that you should probably spend good money and get a nice one. But once you have a nice one, you need to actually attach it to the table. And really what you're looking for is to ensure that the back jaw is perfectly in line with the x-axis of travel. The reason being, when you clamp something into the vise by pushing the front jaw into the piece which holds it against the back, you want to make sure that that piece, registering now off the back jaw, is perfectly squared up to all your angles of travel. So how do we do that? First, we're going to chuck in a dial indicator with the little leg that moves in that motion. And I'd suggest either a half thou or a 0.1 thou indicator. And what we're going to do is we are going to back it up until it touches our vise. You can see as I jog it around in the Y direction, it is moving the dial indicator. So we know we are touching. And really, I made it so that the Z had just that ball underneath the lip of our vise. What we're going to do is we're going to jog the X back and forth to the left and the right, and we're going to watch how that moves. All right, so over that amount of travel, I have about 1.5 thousandths of difference. Or about 1 thousandths. What we can do in order to address that is we can unclamp our vise, or if you're installing it new for the first time, just don't fully tighten it. Now that we are a little loose, we are going to keep moving that back and forth, and we are going to tap the sides as necessary to reduce the swing in that needle to as close to none as possible. So let's give that a go. We're going to jog it a bit. It's really hard to do this while watching the camera, but you get the idea. We're going to tap it until as it goes across the face, it doesn't move at all. I'm going to do this off camera because this is annoying to do, looking through the camera essentially. And then I'll come back and show you what that looks like at the end. I really don't enjoy doing that, but I did that for y'all. I had it trammed before and I untrammed it just to do this part of the video for you. So you're welcome. All right, I've set it on this corner and it's on 0. Now ignore that obvious mar in my surface. I need to address that because I screwed something up. So when we pass over that mar, it's going to jump. But other than that, you'll see I'm no more off than about a half thou. Let's give it a go. All right, in some places it was almost 1/1000th of an inch off, but you'll see at both corners were exactly perfect. So any inconsistencies is in the face of that vise, not in my tramming. So that's good. Other thing to keep note, when you fully tighten those bolts down, it does have the possibility to change. So tighten them a little bit, double check, tiny taps, tighten them a little bit, double check, tiny taps, and then fully tighten them down. Also, anytime you attach anything to your table, you do not want things to rust. So put some oil between the two surfaces, this one and that one. I just use the whey oil that we use for the ways of the machine, and that's going to keep you from having rust in between everything. I'm going to use a set of parallels in the jaws. This is going to make it so that our piece is held perfectly, well, as you can guess, parallel. You haven't seen the piece yet, but here's our scrap. Yes, it has a random hole in the back, but who cares? And what we're going to do is we are going to place it on top of those parallels and in our jaws. Just as it gets tight, I'm going to back it off a little bit, and I'm going to tap hammer as I'm tightening the jaws. And it's not super tight, it's just, for something like this, a small operation, it doesn't have to be super tight, just enough to hold it. Before we start working, we're going to pull this and let it go, and that is going to oil the X, Y, and Z ways. I have been told that it doesn't oil the Z that well, so I also do have a little manual oiler to oil those ways. And obviously the stuff that's in here is whey oil. It's a special type of oil, literally called whey oil. Next, we are going to lower the Z axis so that we can remove the bit that's currently in there. We can go and open the hood, and we're going to loosen up the drawbar. Yours might look a little different. That's because mine had at one point a power drawbar. It's not on here now. It's just manual tool change, but that's why it has these washers and these things here. Yours might not have that. Mine also doesn't have the bar that swings across and locks onto this section to hold it, so I just used 2 wrenches. There is a recommended torque setting for tightening up your collet. I recommend you do it with a torque wrench the first couple of times just to get a feel for it. Yours probably will not take as many turns as mine does because these are compression washers, and so I'm actually adding compression, whereas if you didn't have this weird setup like mine and it was just a standard drawbar, it would just be tightening against static pieces. Finally, last step, to get it out of the spindle, which we will move down here and see. So you're going to hold the tool like that, and we are going to give the top of this a whack, sometimes a couple, and the tool will come out. The first thing that we need to do in order to find our work setup is going to be to use some sort of tool to find our X and Y zeros. I'm going to teach you the cheap way, which is a wiggler. It wiggles. It has a 0.2 inch diameter piece here. We'll learn how to use it in just a sec. I'm going to put the tool back into the collet. I'm going to then tighten up here, and then I'm going to use wrenches to bring that to the correct tightness in terms of torque setting. Over tightening can apparently cause damage. And then we will close and get to work. Wigglers like to run slow, and so we will be setting the RPMs to the slowest that they can go. I generally keep my machine on the high pulley, so that's 525 RPM. and we're going to run it in the forward direction. What we are going to do is we are going to incrementally move this wiggler up to first the side of the piece, and I'm going to, I have a jog wheel, so I'm going to use that, but you can also use the arrow keys on the keyboard if you don't have a jog wheel. Sorry. All right, now that we are fairly close, we are going to increment it by 1,000 using the arrow keys or your jog wheel until that wiggler becomes perfectly in line, and then all of a sudden it'll kick out to the side, either backwards or this way. That's going to be where it has perfectly hit the edge. X kicked at this point, so we know that we are at our edge. However, that wiggler has a diameter of 0.2 inches, so we are to the left of that by half that radius, sorry, half that diameter, so the radius, and that would be negative 0.1 inches is where we currently sit. We're going to go and do the exact same process, but for the Y, and come at it from the front until it kicks. And then again, it will be at -1. I went ahead and put in the first tool that we're going to use for our operations, and that is, for me, tool 7. And we are going to use that to zero to the top of this piece. I like using my fly cutter because it has a nice big sweep. So once I get close, I'm going to, again, switch it to increment by 1,000th of an inch. And I'm going to swing that back and forth until it grabs, and I'm going to back it up back to where it didn't grab and call that 0. There we go. I cannot say this enough, but before you zero your Z-axis, you need to put in the correct tool number. That is because the machine is aware of how long each tool is, and if you zero it with a different tool than the one you actually have in there, you are going to crash your machine. Don't ask me how I know that. So I tell it we have tool 7 in. You see it's a massively different length by about 1 inch. And now I can zero my Z. Let's have a quick sidebar on tools, why having the correct tool mentioned when you zero stuff is important, and how the Tormach uses what's called tool offsets to make it so that you don't have to re-zero the machine for the Z-axis every time you do a tool change. The way that it accomplishes that is it's aware of how long any given tool in your arsenal is, and therefore if we zero out the machine with a known tool length, so T7 for example, if we switch to a completely different tool, it still knows where Z0 is because it's just doing some math between the two of those, and you can run your paths sequentially without having to do a bunch of manual re-zeroing of the Z-axis in between them. So, how does this work? Well, it's as simple as pick a random tool number for what you want to call your tool, give it a name, tell us the diameter, and then tell us the length. It's as simple as that. Now you can call up that tool anytime you want. You should also be entering these tools with the corresponding number in Fusion360 so that as we saw during our CAM phase where we were doing paths, you can reference the correct tool so that when the machine wants you to change, it can actually tell you which tool to change to, and you can assume that those things match. The only real difficult part of this whole equation is getting the actual tool length. There are a couple of ways to do this. I'm going to show you the way I do it, but it does require 2 additional pieces of tooling, and then I'll talk through some cheaper ways to do it if you don't want to buy some extra parts. Here are the 2 tools that you'll need in order to do what I think is the easy way. One is a height gauge. I think this was like 30-40 bucks. And one is a super flat granite. You can get these directly from Tormach with the correct size hole for Tormach tools. I think they're about 50 bucks and then factor in shipping. So about 100 bucks to do this nicely. What this allows you to do, you can zero your height gauge to this surface, put a tool in the slot, and now we know the height of that tool. This one happens to be 28475. Let's try that again. 2848, 28475. So test it a couple times because you want to be as accurate as humanly possible, but 28475 is the length of that particular tool. We can now enter that tool into our database. Another way that you could do this is to pick a given tool, zero it out in your machine, switch out to another tool, and jog this down incrementally until it is zeroed out and see what the difference is. And then you could obviously use that math to figure out your overall tool length for multiple things, as long as you know the tool length of one of them, which you could do very tediously using calipers, etc. You'll see me zeroing out a tool at the beginning of each setup. I'm only doing it once, hence why we have these offsets, but you can use that same sort of style of zeroing to figure out 1, 0, and then find your offsets for other tools from there. Really not optimal in my opinion, but it is doable. All right, we are ready. We have set up our machine with the piece to match how we set our first setup in the software. Those 2 things should be synonymous. We will go to our file. I've plugged in the flash drive, and I'm going to find the folder with all of the paths we need to run, and I'm going to copy it from USB over to my machine. I'm then going to open it and run my first file. You'll notice that T7 is in the machine. I'm going to run a T7 path. I'm going to double click it. And when we click cycle start, the machine's going to get up and going. I recommend holding your finger over the space bar, which will stop movement, and the escape key, which will just turn everything off. For the first couple times you run your machine, just to make sure you're not going to screw anything up. Also, if you have to manually start your coolant like my poor self does, now's the time to manually start that coolant. I'm going to click cycle start off camera so that we can actually watch the machine running. as you saw, coolant gets everywhere. That is why I built this enclosure. I'm going to go ahead and change to our next bit. I'm now going to go to File. I'm going to run my second path. T3 is what I just put in. And mind you, this is how I named them. You could have named them anything. But watch what happens when I hit cycle start. You're going to hear the machine moving the Z-axis to a safe height, but then it's going to tell me that I need to insert T3, which, according to the system, is a 1/4 inch 3-flute flat end mill. And it's not going to run the program, and it's not going to tell me what the tool length is until I hit cycle start. So I've already put T3 in, it's ready to go, but note that if you have a different tool told to the system that is in than what it wants to run, it's going to give you warnings. Let's watch. And remember, this is going to run 3 independent paths with that same tool. Nice smooth surfaces. We've got our little circle. I'm going to go and again, I'm going to do the same process I always do to change out the bits. I'm going to lower the Z-axis so I can access it, unscrew, tap hammer, switch bit, re-screw, and then we'll be ready to do the top chamfer. So while that might have been fun to watch, we didn't really learn anything from the second 2 paths than we did from the first one. Here's the last little key piece of golden nugget that we are going to learn today about actually running paths. We are going to unclamp our piece because we are about to flip it over and run the back. Now, I've got a lot of surface to grab onto now, and so I'm actually going to go and change out the parallels so that I can get something where this sits a little deeper in there, not only to have a better grip, but also with a deeper grip, I'm going to grab more surface and I'm going to reduce the risk of marring the aluminum because this is stronger steel material. So when picking your parallels, you need to be aware of how much material you're going to be pulling off and how much material you're going to be leaving. You also need to make sure that the parallels sit flat and that there's no chips that are in their way. So those parallels are too deep. I'm gonna have to go one size up. I wipe off the bottom, and then a lot of times what I'll do is I'll actually use the parallel as almost a scraper to push along, just in case there are any chips along that edge. It'll clear them out for me. There we go, that's much better. So again, we're going to tighten, and as I get to the point where I feel it grab the piece, I'm going to do a light tap as I tighten. And again, it doesn't take a lot of pressure unless you're getting super aggressive, which we're really not here. All right, I'm going to put the wiggler back in, and we're going to talk through setup again, because it is a little different this time. Remember that this point used to be over here before we flipped it, and that is now our 0 point based on our second setup. So I need to find that edge and that edge. just kicked out, but we are in front of, to the right of our 0. So that is now at actually positive 0.1. I'll go into that. From our edge, so this is negative 0.1 in the Y. I'm now going to switch out to my fly cutter, tool 7, and do the same zeroing process on that edge for the Z. I have made sure to tell the machine that tool 7 was in. I zeroed it. I'm going to go run my path for the back facing and cycle start. There's our widget without the excess on the back. I'm going to put in the chamfer and we'll run our last path and then we'll look at it. Let's go ahead and remove our part. We are done. We have a nice circle hole. We have a nice deep top chamfer as modeled. We have a nice finish on our back and a very small back chamfer as modeled. If we were to mic this out, it should be accurate to within a thou or two. I say a thousandth or two simply because a wiggler is known to have an accuracy of about a thousandth of an inch, some of them a half thou, and so that can introduce some inaccuracy. But a thousandth of an inch for most people's use cases is pretty good. And just for fun, let's prove that out. If you are done today, it's time to turn off the machine. There's an order of operations for turning it off, just like there is for starting. First, we kill the actual machine. Then we can kill the computer. I actually don't have my computer hooked up to that switch for the same reason I don't have my coolant hooked up, because this machine is an old beater and neither of those outlets on the bottom of this enclosure actually work. We will go exit. We did e-stop the machine, and now we can go turn off power to everything. One of the things that was the biggest black box of mystery to me when I first started was coolant. It came with a fog buster, which is that little thing hanging there that mists essentially coolant, and that uses a different type of coolant. But if you're doing anything serious, you need to look into getting flood coolant. So I was given a tiny bit of this Synergy 735. And let's walk through what I've learned. So there is a refractometer factor of 1.4. What this means is when you mix the chemical with distilled water or reverse osmosis water, because you want very clean water or else this stuff doesn't work right, you're going to have to use this little tool called a refractometer, and it's going to tell you how much coolant to water ratio you have. This has a factor of 1.4. So whatever I see on my refractometer, which I'll show you in a second, you need to divide by 1.4 to get your actual concentration percentage. This is a refractometer. You take some of the liquid from your coolant tank and you put it on this slide. You are then going to take this cover, mine falls off all the time, and I have it on backwards, and squish down the liquid. And then you're going to look through the eyepiece. Let's see if we can't get it to show. So there we go. And you'll see that I have a concentration of about 19. If we divide by 1.4, which is our refractometer factor, I'm looking at over 10% concentration, which means I need to thin this out a bit, which we will talk about in just a second. This is where the coolant comes out of the machine after use. It filters out any chips, and then this is where it feeds this sump pump, and that cable goes up to feed the actual coolant. The reason my coolant is oftentimes overly concentrated, as we just saw, is because I have a dehumidifier running in my shop so that my tools do not rust. However, I have found that that also pulls the moisture out of my coolant mix, and that is why I have started putting this tarp over the entire coolant area, and it's helped, but I still get a decent amount of evaporation, so I'm gonna have to find a good way to do this. But keep that in mind, that you do have to check your coolant every now and then. It's expensive stuff. You get to reuse it for a decently long amount of time, especially if you go synthetic. The other stuff, if you're not an everyday user, it can go bad and start to stink like rotten eggs. So if you're a hobbyist like me that runs your machine just every couple of days, if that, go synthetic, you guys.